Hello viewers, welcome to another lesson of ours. Today we are looking at forces, and I am your presenter, Buba Tamba. Like I said, we are looking at forces today, and I am tempted to ask, what is a force? So every day we undergo certain activities, or we do certain activities. We turn doorknobs, we walk around, we apply brakes for some of you that ride motors or vehicles, right? We apply brakes on bicycles, you know, and a host of many other activities. And in each of those activities, basically what we are doing is simply the application of a force. Because each time we apply a force, of course it causes an effect. So basically, we want to look at what forces are, what causes forces, obviously, and the effect of forces. The type of forces we would also be looking at, right? What are forces? For example, if you look at, seeing on the slide, we have different types of objects. We have a catapult, we have a human finger, you have gears, we have rubber bands, we have the human leg, right? Each of these objects here can actually create a force which can eventually create an effect. So we say forces are either a pull or a push. As you can see on the slide, forces have direction, and that is why we call them as vectors. Forces are vectors, and forces affect objects by, one, making them move or stop, just like I said in the introduction. By also accelerating an object, changing its velocity or speed or direction. Forces can also hold them together, like the force, that electrostatic force that exists between particles of the same substances, for example, and even of different substances. And forces can also cause deformation and even destruction. For example, if I have this calculator here and I smash it hard with an object or even with my palm, I can actually destroy it. And that is also an effect of a force. So we say, since forces can change the speed or direction of an object, we say that forces cause change in velocity. So forces actually cause acceleration. Now we also want to look at units of forces. In science and most of the world, force is usually measured in newtons. In the US, force is usually measured in pounds. And you can see the conversion there. 1 pound is given as 4.448 newtons. And a newton, the amount of force required to pick an average size apple from the ground to, let's say, a tabletop, that would equal 1 newton. So I think you can relate. We will learn how the newton relates to other physical units later in this unit. We would also look at net force. Okay. For example, if I have a calculator or an object on this tabletop here and I apply a force. If I apply a force on it, obviously I am causing the calculator to move. Right? I'm causing the calculator to move. So if I apply an equal and opposite amount of force on the other side of the calculator, what happens? The calculator does not move because the force is balanced. That is what is called a balanced force. And just like this also, if the calculator is here, it's applying a force that goes direct into the table, and the table is also applying a force that comes onto the calculator, which is the reaction from the table. And that also is balanced. The force that the calculator is exerting on the table would be the weight of the calculator itself, and the normal reaction would be the force that comes from the table end, and that is why the calculator at this point is not moving, right? So those are some balanced forces. However, if I just push it and there is no counterbalancing force, obviously the force is not balanced, and there is a net force, which is causing the calculator to move. So those are some of the things that we will be looking at. When you approach problems that have to do with forces, essentially you need to do what is called the free body diagram. If I have an object on this tabletop here, and of course forces are acting on this object, you need to draw the free body diagram. the free body diagram will help you identify all the forces that are actually acting on this particular object, right? And for example, let's have that as a quick example. To understand how forces affect an object, it is important to draw a picture of the object or simple representation of the object like a box or a dot, and all the forces acting or affecting that particular box or dot. This picture is what is called the free body diagram. For example, I'll use this calculator as an object. Now this object is resting on this table here. Now the free body diagram of this object will help you identify all the forces that are actually acting on this object. That will also help you to know how you approach this whole thing. So if I have, let's say this is my tabletop and I have my calculator resting on this tabletop. Now what the free body diagram does is to show all the forces that are acting on this calculator. One of the forces would be obviously the weight of the calculator itself, which points downward. You cannot draw the free body diagram without indicating the arrows, because the arrows is what shows the direction of that particular force. And there is also a normal reaction which comes from the tabletop end, and that points upwards. And that is what is called R. In some books they would just write N, but it's all the same if you understand what the issue is. And this is why the calculator now is seen to be balanced, because these forces are cancelling out each other. The effect of one force is being cancelled by the other force. If I introduce another force here, let's say a pushing force. Let's say I am pushing this calculator this way. If I introduce another force this way, then the calculator is being pushed in that direction. And because the calculator is also in contact with the tabletop, certainly there is what is called friction. Whether you see it or not, there is always what is called friction. In questions, if the question doesn't mention that the surface is perfectly smooth, then you always have to know that there is friction. If they read a question to you or they give you a question and ask you to find certain forces, when these particular objects are in contact, then you should always know that there is friction. Friction is always available, right? So the frictional force will always oppose the motion of this particular object. Let's say I'm moving the calculator this way. If I am pushing the calculator that way, the frictional force would act in this direction. The frictional force will act in this direction. That means to oppose the motion of the object, right? However, if there is another force that is acting in that direction, let's say I'm trying to push this and there is another person or something also trying to move it this way, there is another force also which is blocking it coming this way. So if the net force, let's say my pushing force, is greater than the addition of this counter force that is coming from here plus the frictional force, then the object will be able to accelerate. But if they are equal, then they will balance each other out. They will balance out, and obviously the object will still remain in its position or in its rest state, right? So this is what is called the free body diagram. A free body diagram is used in order to show all forces acting on an object. Drawing free body diagrams can help when solving for unknown forces, finding the motion of an object. Now, free body diagrams. 1. Draw and label a box or a dot to represent the object. Here, we'll use a box, just like I demonstrated earlier on. 2. Draw an arrow from the box pointing in the direction of one of the forces that is acting on the object. We say label that arrow with the name of the force. Number 3, repeat for every force that is acting on the object. Try to draw each of the arrows to roughly the same scale, bigger forces getting bigger arrows. For example, if you look at this diagram here, this is an object, and there are two forces that are actually acting on this object. One of the guys here is bigger than the other. So they are trying to push the box, and that is what the explanation here is. You can see that this is the free body diagram, that is the box, and this guy here, this arrow here, obviously is the big guy who's trying to push the box in that direction, and the other guy, the small guy here, will be this guy, the little man, who's trying to push the box in this other direction, right? And so what will happen here is there is going to be a net force, just from face value. there is going to be a net force because these two individuals are different in size and obviously they are going to be different in force. So there is going to be a net force and the net force will act in the direction of the bigger force. Now this is the bigger guy. The net force obviously here is going to act in the direction of the bigger force, which will eventually cause what is called acceleration, and that is what we have here. Okay, like I was saying, you can clearly see that the bigger man here is being represented by the bigger arrow, and the little man here, or the small man, is being represented by the little arrow here, or the small arrow, right? That way, we denote the type of forces, or the type of forces that are actually acting on this object. Now we say draw a separate arrow to show the likely direction of the acceleration of the object. This is also a very important point, like I was explaining. So the effect of these two forces, obviously, you realize that there is going to be a net force, and that is what is going to create what is called an acceleration. And the acceleration that is going to be created in this system here is going to go towards the smaller guy, the little guy. And therefore, you need to create another arrow for acceleration that will point in the direction of the small guy, that is here. Because the big guy is here and is moving the object towards that direction. And so the direction of the acceleration would also point in that manner. So forces and acceleration point in the same direction. Net forces cause an acceleration which also point in the direction of the force that is actually creating the acceleration itself. Now, if I ask you to draw the free body diagram for an object being pushed down by one force while being pushed up by another force of the same magnitude, I think you should be able to do that. And I give you another one. Draw the free body diagram for an object being pulled to the right by a force. And finally, draw the free body diagram of an object being pulled to the right by one large force and one small force. I think you'll be able to do that. That is what we have here in summary. So we have the free body diagram of an object being pushed up and another force pushing the object downwards. That takes care of number one. And number two, you are asked to draw a free body diagram of an object being pushed to the right. And that is what we have here. And finally, number two, you are asked to draw the free body diagram of an object being pulled by a big force towards the right and also a small force towards the right. And that would also have been taken care of by this diagram, right? Now we want to look at what is called a net force. A net force is just what I have explained. So if two forces are acting on an object and these forces are not balanced, obviously there is what is called a net force. Just like in the small man, the little guy and the big guy case over there. So the sum of all forces acting together is called the net force. The net force is usually written as sigma F. And the Greek letter sigma here means the sum of. It means the total number of forces that are acting on a particular object. Sometimes sigma F is written as F net. So in books or wherever you see F net, you should always relate it to sigma F. That means the total number of forces that are actually acting on an object. The first step in determining how forces will affect an object is to determine the net force. Yes. If you want to know what really forces will affect a particular object, you always need to determine what the net force of acting on that particular object is. If you don't do that, then it will be difficult for you to be able to establish what the effect is going to be. Whether it's going to be a push, or it's going to be a pull, or it's going to be a crash, or whatever. You need to know that. By adding up all the forces acting on the object. Remember that force is a vector. This is a very important point. So, in some cases, you see people adding vectors. You see people adding forces as scalars, but they are not actually scalars. Scalars have only magnitude. But as you can see in our previous discussion, forces have direction and they also have magnitudes. And anything that has a direction and also has a magnitude is regarded not a scalar but a vector. So when you add forces, you have to add them like vectors. Vectors have direction and they can cancel out. For example, an object is being acted on by a 20 Newton force to the right, which we call F1 for example, and a 30 Newton force also to the right, F2. What is the net force on the object? First, we'll draw the free body diagram. Start with a dot to represent the object and draw arrows to represent the forces. The direction of the arrows represent the direction of the forces, and their length is roughly proportional to their sizes, right? So that is what we have here. This is our challenge, and we will just go ahead and draw that, right? For example, it says a 5 kg object is being acted on by a 20 Newton force to the right and a 30 Newton force also to the right. So let's say this is 5 kg. We have our force F, which is 20 Newtons, which is acting on this particular object to the right, and another force is also going to act on the same object and also to the right. So what is going to be the effect of this particular, the effect of those particular forces that are acting on this object, right? Let me do a quick explanation here. So for example, we have this as our, if you have this as your F1, for example, which is acting on this object, let's say this is the dot here, that is the object, and you have another force, which is, this is, let's say 20 Newtons. You have another force, which is also acting on this object, and that is, let's say 30 Newtons. Maybe I should, let's say 30 Newtons up to here. That's 30 Newtons, and that is, we call that F2. F2, and they're both pointing in the same direction. What we do here is we take F2 and add it to F1 by simply doing the resultant here. I'll choose a different color for that. So we will first draw our object here, and then we would add we would do our F1 here, F1, and then on F1 we add F2, and that will give us our F net or summation F. That is the total number of forces that are actually acting on this particular object, right? So as you have seen, as I was explaining, that is what we have here, F1 and F2, both pointing in the same direction. And you can see the result is F1 plus F2 also pointing in the same direction. Now this would be the resultant or the summation, that is the F net. The total number of forces acting here is the summation of F1 and F2. That is what we have, right? Okay. So we will take our first example. It says two forces act on an object. One force is 40 Newtons to the west, and the other force is 40 Newtons to the east. What is the net force acting on the object? So, like I said, the free body diagram. First, always the free body diagram. Without the free body diagram, you will not be able to know what to do. This is 40 Newtons to the west. This is our west. And the amount of force there is 40 Newtons. And we have another force. Let's say, would yellow work? Or maybe black. We have another force also acting to the east. Also 40 Newtons to the east. So 40 Newtons also to the east. And this is east. So now it is asking you, what is the net force acting on the object? What is the net force acting on the object? So it's just simple. You add 40 Newtons. The direction here, we would take the direction, the west direction to be negative, and we will take the east to be positive. So if this is negative, we will add minus 40 Newtons plus 40 Newtons. And that is going to give you what? This is actually plus 40 Newtons. That is going to give you 0 Newtons. So the net force acting on this particular object will be 0 Newtons, and B would be the right answer, right? B would be the right answer. This would be our right answer, 0 Newtons. Number 2, two forces act on an object. One force is 8 Newtons to the north, and the other force is 6 Newtons to the south. What is the net force acting on the object? Again, you have to draw the free body diagram. This is your object here. This is your object here. One force is 8 newtons. It's 8 newtons to the north. This is north. And the other force is 6 newtons to the south. 6 newtons to the south. What do you do? The sign, our sign, according to our sign convention, the south is negative and north is positive. So what you do is you say plus, or you just say 8. Okay, you can add plus 8. It doesn't matter. Say plus 8 minus, because south is negative, plus 8 newtons minus 6 newtons. What do you get eventually? You get a plus 2 newtons. A plus 2 newtons. Plus 2 newtons. Do we have plus 2? Yes, plus 2. C. So option C would have been the right answer for this particular question, right? Now, like I explained, balance forces. When forces are acting, or when forces are equal and opposite in direction, we say that the forces are balanced. If we start a tug of war with balanced forces, no one wins. So if you have equal amount of people on one side of the rope to the other side of the rope, and they're trying to balance out each other, they're trying to pull each other or pull each other across the winning spot, obviously if their forces are equal, nobody will win. Nobody will win. There is always going to be a stalemate. However, if you have unbalanced forces, there is going to be a change in the direction of the net, in the direction of the forces. Obviously, the different forces that are acting, there is going to be what is called a net force, and the net force will act in the direction of the bigger force, obviously. So when forces are not equal and in opposite directions, we say that the forces are unbalanced, like I demonstrated earlier on. If you have a force of 2 newtons trying to act on an object of on an object, and you have another counterbalance counter force which is about 2 newtons, the other one is 4, the other one is 2, obviously, and in in opposite directions, obviously there is not going to be a balanced force. The force is going to be unbalanced, right? So in a tug of war, for example, and of course the net force is not going to be 0. There is going to be a net force, just like we did in the previous example. In a tug of war, the side with the largest force wins. The net force is pointing their way, like we did the small guy and the big guy case, right? Now, Aristotle and Galileo, these are two great philosophers and scientists that lived a long time ago. Galileo lived about 400 years ago, but Aristotle was way back, about 2,400 years ago. So these are people that were philosophers and great scientists that have contributed immensely to our understanding of science today. Now we look at their various takes when it comes to forces, right? These are some effects of forces. What does force do actually? The first thing, forces can get objects at rest to move. If I have this object at rest here, if I apply a force, the object can begin to move. Forces can also stop object moving. If this object was moving like this, if I apply a certain force, obviously the object will stop moving. Forces can also make moving objects to speed up. If this object was moving at 2 meters per second, I can increase the force and the object will speed up. These are all effects of forces. Forces can make a moving object slow down. This object was moving. If I apply a certain force, the object can slow down. You see that? These are all effects of forces. Forces can also change the direction of an object. So if this object was here and I apply a certain force on this object here, it can either be a twist, like we said in the beginning. A force can either be a twist, can be a push, can be a turning or whatever. So if I apply a twisting force here, this object will turn, right? If I twist it, it can also go in the direction of the applied force. It will also twist, right? Forces can keep an object moving. So if I apply a constant force on this object, then the object is going to stay in motion. It's going to stay in motion. That is what it means, right? We all have an intuition about how objects move. Our beliefs are hard to change since they work well in our day-to-day lives. But they limit us in developing an understanding of how the world works. In our experience, this was actually said by Aristotle, objects must be pushed in order to keep moving. So a force would be needed to have a constant velocity. This is what Aristotle claimed in his series of books entitled Physics, written about 2,400 years ago. Galileo, who is also another Italian scientist, if you remember Galileo, who did so much work about the spherical nature of the earth and some other things. It's a beautiful history about Galileo, if you could read it. Galileo and the political establishment in Italy back then. About 400 years ago, another scientist and astronomer, Galileo, proposed the following thought experiment, which revealed another perspective. Now, imagine two perfectly smooth ramps connected together by a perfectly smooth surface. In physics, when we talk about perfectly smooth surfaces, these are surfaces wherein there is no friction at all. Friction has been completely eliminated. So imagine two perfectly smooth ramps connected together by a perfectly smooth surface. If a ball is let go at the top of the ramp, for example, at the top of one ramp, what will happen? So I ask you, if I release this ball from here, from the top of this ramp here, what do you think is going to happen? Right? Now let's see. The motion of the object. The object is moving. It was released. It was actually here. It was released from this point. And now the object is moving, and it's moving, and it's moving, and it's moving. If a ball rolls down one ramp, it keeps rolling up the other side until it reaches the same height. This is talking about energy conservation, which I am sure most of you have been introduced to in your earlier grades. Right? Now repeat the experiment, but make the second ramp less steep. Look at this. Take a good comparison between this side of the ramp and that other ramp. This side is steeper than this other side. Now, what is going to happen again? The question is, if I release a ball from this point here, what do you think is going to happen? What do you think is going to happen? Right? Look at the motion of the ball. The ball was here and it was released at this point. It is here. And we expect it to go that way until it attains the same height. But this time around, it is going to cover more grounds than the previous one. You see that? It will still keep rolling until it reaches the same height, but it has to roll further. Just like I was explaining, it has to roll further. Now finally, make the second ramp flat. What will happen to the object? What will happen to the object here? This was the initial height of the object. Now if I release it from this point, what do you think is going to happen to this object? What kind of motion is this object going to exhibit? That is also another question. Now let's see what happens. The object is moving, and it's moving, and it's moving, and it's moving, and it's going. The object will keep rolling forever if no external forces is necessary. Sorry, the object will keep moving forever. And in this case, no external force will be necessary to keep the object moving. Right? The object will keep moving. Because now, there is no need for any other external force. The object is not actually going to climb up, because if it was going to climb up, there is going to be an external force. Remember? These are perfectly smooth ramps, so there is no friction. Friction has been eliminated, but there was going to be an external force that was going to come. Where was that going to come from? Gravity, obviously. Anytime you talk about height and forces, gravity must always come to mind. It's not that Aristotle was wrong. In everyday life, objects do need to keep being pushed in order to keep moving. Push a book across the table. When you stop pushing, it stops, obviously, which confirms Aristotle's point. Aristotle is right in terms of what we see around us every day. It's just that Galileo and of course Newton now begin to imagine a world where friction was present. Because in the entire world, there is no perfectly smooth surface. By that I mean there is no surface that you can create that does not have friction at all. There is no such phases. So it's an imaginary situation, right? Friction represents an external force acting on the object. And so if I have, for example, this box and I am pulling it, obviously if I do not maintain the constant force that I am using to pull that, obviously it will come to an end because there is friction acting on it, right? So we say friction represents an external force acting on the object. Just as your pull or push, it is an external force. Like you can see, if this guy here is trying to pull this box towards the direction, and the frictional force is trying to oppose the movement of that object, right? Now we want to look at Newton's force law. That ramp situation, I did mention that if the object was released from this surface, if the object was released from this point here, in this situation here, if the object was released from here, the object was going to go like that, and it will never come to rest. It will never come to rest. Why? Because these are perfectly smooth surfaces. These are perfectly smooth surfaces. But then, that is in an imaginary situation. In real life, there is no way that you can create a perfectly smooth surface, a surface that is completely free of friction. So therefore, this object will at some point come to rest. But you always have to have it at the back of your mind that we are now dealing with a surface that we have regarded as perfectly smooth, and therefore friction has been eliminated. And so the movement of this object basically is going to continue in that order forever and ever, right? And this will now lead us to Newton's force law. Newton actually postulated that when an object is in motion or is at rest, it will continue to be in motion or continue to be in rest, unless and until it is being acted upon by an unbalanced force, right? And in the situation of that ball, and on the, of course, the flat ramp, obviously there is not going to be any unbalanced force, and so the object is going to continue moving, right? Galileo's observations were more fully formed in 1687 by the father of physics, Sir Isaac Newton, who called this observation the force law of motion. Try each of these. What can you conclude? Place a card on top of a glass and a stack of pennies on the card. In our case, we would call them coins. Flick the card horizontally. What happens to the pennies, or what happens to the coins? If you have coins, a number of coins, maybe you can try this. You place a small card on top of a glass bottle or a glass cup and try to flick it horizontally and see what happens. Now give a battery-operated air pug a push on the floor, on the clean floor. Describe the motion of this pug. And the third point would be place a heavy book on the floor. Place a toy car on a cart against the back edge of the cart. Roll the cart at the book. What happens to the toy car? These are all things that you could try at home, right? Hopefully you observe something like this result. 1, the coins or the pennies did not move with the card. It was only the card that actually moved. The pennies also moved, but their directions differed. Their directions were not the same, right? They fell into the glass. That means the pennies actually fell into the glass, but the card was actually moved horizontally. The pug just kept moving. Its speed and direction did not change until it hit something. The toy car, however, traveled with the cart. But when the cart was stopped by the book, the toy car kept going. How can we summarize this? An object at rest remains at rest, and an object in motion remains in motion along a straight path or along a straight line with a constant speed, unless acted on by a net external force. An object maintains its velocity, both speed and direction, unless acted upon by a non-zero net force. Having zero velocity or being at rest is not special. It is just one possible velocity. Newton's first law is also referred to as the law of inertia. The word inertia comes from the Latin word iners, which means idle or lazy. Inertia is the tendency of an object to resist any change in motion. Which has, okay, now look at this diagram. You have you have a situation here of two objects. One is a bowling ball and the other one is a tennis ball. The bowling ball is far bigger than the tennis ball. And the question is, which has more inertia? And by definition, we say inertia is what? Is the tendency of a body to oppose motion. That is what inertia is. The reluctance of a body to remain in its position. That is what inertia is. So we say a tennis ball or a bowling ball. And why? I'm asking you, which one has more inertia? Is it the tennis ball or the bowling ball? Which one has more inertia? And I'm asking you why. The answer is the bowling ball. It has more mass than the tennis ball and requires more force to change its motion. In the absence of an external force, a moving object will A, stop immediately, B, slow down and eventually come to a stop, C, go faster and faster, and D, move with a constant velocity. In the absence of an external force, a moving object will, you remember, in the absence of an external force, let's say this here is actually the ball and the ram situation. Now this is our ball, for example, and this is our ram, and this object, this ball is actually moving on the ram. And remember, the question is telling you that there is no external force, meaning friction has been eliminated, meaning gravity has been eliminated, meaning every other force, possible force, has been eliminated. What is going to happen to this object? Is the object going to stop immediately? Or is the object going to slow down and eventually come to a stop? Or is the object going to go faster and faster? Or is the object going to move with a constant velocity? In this case, B would have been the right answer. The object would be moving with a constant velocity, right? Because there is no external force. When the rocket engines on a spacecraft are suddenly turned off while traveling in empty space, the starships will A, stop immediately, B, slow down and then stop, C, go faster and faster, and D, move with a constant velocity. Still the same? The answer would be, it will go with a constant velocity. And D would have been the right answer. A rocket moves through empty space in a straight line with a constant speed. It is far from the gravitational effect of any solar or planet. Under these conditions, the force that must be applied to the rocket in order to sustain its motion is equal to its weight, B, 0, C, dependent on how fast it is moving, and D, equal to its mass. A rocket moves through empty space in a straight line with constant speed. Remember, the speed is constant here. It is far from gravitational effect of any star or planet. Under these conditions, the force that must be applied to the rocket in order to sustain its motion is equals to its weight is 0, dependent on how fast it is moving, and D, equal to its mass. Here we don't need to apply any force, and the rocket will maintain its movement, its velocity, right? Number 6, you are standing in a moving bus facing forward and you suddenly fall forward. You can infer from this that the bus's A, velocity decreased, B, velocity increased, C, speed remained the same but it's turning to the right, but the bus is turning to the right, D, speed remained the same but it's turning to the left. Now look at the question critically. It says, you are standing in a moving bus facing forward. This is the moving bus, for example, and you are facing forward. And you suddenly fall forward, and you suddenly fall forward. You can infer from this that the bus's velocity decreased, the bus's velocity increased, the speed remained the same, but it's turning to the right, and the speed remained the same, but it's turning to the left. So what happens is the bus's velocity actually decreased, because if you are in a car and suddenly the velocity decreases, you tend to lurch forward, right? Now you are standing in a moving bus facing forward. This is a similar question, and you suddenly move forward as the bus comes to an immediate stop. What force caused you to move forward? What force caused you to move forward? A, gravity. Gravity. B, normal force due to your contact with the floor of the bus. C, force due to friction between you and the floor of the bus. And D, no force at all. So the right answer would have been the normal force due to your contact with the floor of the bus. And number 8, which object has the greatest inertia? Which object has the greatest inertia? So we have a car, for example, we have a tennis ball, we have a person walking, and we have a moving freight train. Obviously, you cannot compare a train to any of these objects here. So the right answer would be D, right? Which object has the greatest inertia? Again, a similar question: a car, a tennis ball, a freight train at rest, and a bicycle moving. A car, a tennis ball, a freight train at rest, and a bicycle moving. Even if the freight train is at rest, it still has a more inertia than the rest of the objects, right? Which object has the greatest inertia? Moving tennis ball, a moving tennis ball, that is A. B, tennis ball at rest, and C, both have the same inertia. They all will have the same inertia. That is C rather. Both of them will have the same inertia. The moving tennis ball and the tennis ball at rest is still the same tennis ball. Has the same inertia. A ball at rest will start moving when it is acted on by two equal forces pointing in opposite direction. Pointing in opposite directions. True or false? A ball at rest will start moving when it is acted on by two equal forces but pointing in opposite directions. True or false? I think the right answer will be false. It will not move because the forces will balance out. The effect of one force will balance out the other, right? Now we want to look at inertia and mass. A bowling ball requires more effort to get going, stop, or change direction. That's because the bowling ball had more inertia than the tennis ball. There is a way to measure this inertia, which is the mass of the object or the ball. Mass is a measure of how much matter there is in an object. Mass is often measured in kilograms. In most labs and problems, we will be working with mass in kilograms. Sometimes we may also measure mass in grams. So that will bring us to the end of this lesson until I come your way in the next video. Thank you very much.